What's happening here? Sorry. I'm having technical issues, whatever you want to call it. Here we go. Today we are going to do chapter 6, at least chapter 6.1 and 6.2. There are a lot more sections to it, but we only need to do those two sections for the midterm. And then at the end of today, I want to go over some of the details to do with your midterm exam. And I'll be open for questions and things like that as well. So let me zoom over to our whiteboard. We are cool? Now just move my camera a little bit. That's weird. I'm just adjusting the gizmo. There, we're good. Right. Can I up it or down it a bit, whatever it is? There we go. Okay, so we are going to be looking at chapter 6, at least the beginnings of it. It deals with a very interesting property, or a very interesting distribution. It's called the normal distribution. We are going to look at what does it look like and how can you use it. And it's used a lot. You'd be surprised by how many things use this thing called the normal distribution. So let me show you one. You've actually met normal distributions before, you just didn't know that's what they were called. Now, when I draw this shape, it's really made up of lots of little rectangles, right? It's really a histogram, but it's a short way of doing it. What would you call that shape?
A parabola?
I'm thinking more left skewed, right skewed, symmetric, that kind of thing. What would you call it?
Symmetric.
Yeah, symmetric shape, right? Now I want you to imagine that we collected all the data on a population. So that's where we kind of imagine that we've done. So we've collected all the heights of American adults, right? Or all the weights of people who live in Bremerton, whatever the population happens to be. Very often, the data ends up looking like this when you make a graph of it. Can you imagine the data ends up being symmetric, essentially? And that, symmetric is its name, but it's also going to be called a number of other things. So you might look up notes in, online. And so I want to try and give you some of the equivalent names. You'll find it's sometimes called a bell-shaped curve. It's, I believe this textbook calls it mound-shaped, which is fine. It's just a name for it, right? It's also called a normal distribution curve. So what's interesting about this kind of distribution? Well, if you go to the center of the hill, isn't that where the mean and the mode both live? Great. Now, since this is a population, what funny little Greek symbol do we use to represent the mean? It's a very short word, starts with an M sound.
Mu.
Yeah. Right. So far, so good. So a normal distribution is a symmetric distribution like this. And the center of that distribution, right in the middle, is going to be the value of the mean. That's where the mean lives, right? Right in that point there. Now, I think I'll do another one. There is a little bit more information that a normal distribution has. So I'm going to go and do that guy. And I'm going to call it, yeah. If you had two distributions, and one of them looked like this, let's say that's at 30, and the other one was also at 30. And the other one looked like that. Which one of these two would have the biggest standard deviation? I'll give them names. Would number 1 have a big standard deviation, or would number 2? And remember, what standard deviation measures is how spread out things are, right? So which one of those has got the larger standard deviation?
Number 2.
Yeah, right. Wider, for want of a better word. Now, I want you to imagine and I'm coming back to that guy. Now, we had a distribution, and it was the IQs of American adults. And the mean of the population was 100. And the standard deviation of a population uses that little guy. I guess I should put the Greek letters next to it so that you can remember what to call them. Anybody remember what that funny guy is called? It looks like a zero with a hat on. Starts with an S. Last chance. It's called sigma. And let's say that this has a sigma of 10. Now, can you imagine I gave you some values here, and it would look something like this. So what you can see from my very crudely drawn picture is that the IQ of 100 is probably going to be the most likely IQ that people have. But aren't there some people with an IQ of 120? There's a few people with an IQ of 130, and not that many people with 80, and even less people with an IQ of 70. Can you get an overall idea of the distribution, in this case of IQs, of some American adults? Now, that guy there is the mean plus 1 standard deviation, because the mean is 100 and you add 1 standard deviation, so you get that guy. And this guy here is the mean plus 2 standard deviations, and this one here is the mean plus 3 standard deviations. And if you go the other way, you get the mean, take away 1, the mean, take away 2, and lastly, the mean, take away 3 standard deviations. This is the typical shape of any normal distribution. So if you go and collect Americans' heights or weights, or Scottish people, how much alcohol they drink, or whatever it is, it will very often have this normal distribution shape to it. And not only that, won't the middle of the hill, the tallest part, be where the mean lives? And do you notice that these 3 guys going either side? Typically, almost all the data is within 3 standard deviations of the mean. And that doesn't matter if it's to do with Americans' height or weight or Scottish people's alcohol consumption. This is a standard property that all normal distributions have. And it's quite surprising that that is true, because you could imagine tons of different versions of this shape. You made little skinny tall ones and fat wide ones, you know, they all have that symmetry shape, right? But you can imagine how many different versions of symmetry shapes there could be. Every single one of them, the middle is where the mean is, and if you go 3 standard deviations either side, pretty much every single number, you know, every single data point is inside that range. It's kind of interesting fact. So suppose I had a population and the mean was 65 and that the standard deviation was, say, 3. If I wanted to draw only based on that and the fact I know it's a normal distribution because I was told it was, I can make a pretty decent representation of what that might look like. Right in the center is going to be 65. Now I try my best to draw a nice symmetric curve. And then all I do is go 1, 2, 3, and back 1, 2, 3. And for each one of these little marks, just add a standard deviation. In this case, it's 3. So that guy's going to be 68, 71, and 74. Take away 3, take away 3, and take away 3. And I managed to draw this entire picture, which kind of shows you everything you need to know. Can't you tell that the mean here is 65? With a little counting, can't you figure out what the standard deviation was? And can't you also see that almost every single person, imagine this was a test, almost every single person in the class would have a score somewhere between 56 and 74. You can even do this property in reverse. Based on this shape, you should be able to tell me what the mean of this population is, and you should also be able to tell me what the standard deviation is, even although I haven't told you one person in that population. I haven't told you anything about anybody. Just gave you this picture. Okay, what's the mean?
90.
Standard deviation.
2.
Would you agree that is dead easy to get? You don't need to overthink it. You don't need to do, 20 minutes hitting buttons in your calculator with a whole load of data. Can you see you can simply just get the information straight from there? And if I tell you this, you can draw that picture. If I give you this picture, can't you tell me this? You see, it's a two-way street. The information's contained in both directions. Well, that would be interesting if that was all that you got. But there's even more structure in a normal distribution than just what I've showed you. I'm trying to find my old guy if I can. Oh, here it is. Remember this generic one that just had basically no numbers, but it did show you the pattern. Can you see the pattern I'm talking about? 1 standard deviation, 2, and 3. It's just written in a very generic kind of way. We okay with that? Right. Now, wouldn't it be kind of cool? Well, I'll tell you, and I'll say it as kind of cool. Do you know if you go 1 standard deviation either side of the mean? So essentially you look at only people in that range. So in this picture down here, it would people who have an IQ between 90 and 110. %68% of all the people in the population will be in that range. It's amazing that it's the same number, because you can imagine a mean of 50 and a standard deviation of 2, right? A mean of 1,000,000 and the standard deviation of 50,000, right? Big numbers, tiny numbers, as long as it's got a normal distribution, right? Symmetric, and it looks like this. If you take the mean and you add a standard deviation, and then you take away 1 standard deviation, 68% of the data lives in that piece of the world. That's pretty amazing that's a property that's true. You wouldn't have guessed it. I mean, you would probably think that, tall, skinny ones and big, fat, wide ones, the numbers are going to be different, but they're not. it doesn't even stop there. Do you know if you go 2 standard deviations away from the mean? So 2 standard deviations away from the mean would be you'd start, what, at 80 and you'd finish at 120. So can you imagine going from here all the way to here? Well, 1 standard deviation, I'll have to squeeze it in, is 68% of the people. 2 standard deviations away from the mean, right? So if you go IQs between 80 and 120, right? If you go from this mark here to this mark here. So if you go from here to here, right? Everybody in that range, 95% of all the people have that. So in this case, and by the way, this is actually accurate data. Do you know that, I don't know if you've ever done IQ tests, they were popular, you know, for a while, and then they kind of went out of flavor, right, kind of thing. But the typical IQ test is a mean of 100, right? So an average American or Chinese or whatever country you come from, it's about 100. And the standard deviation is about 10. So I can tell you right now that 95% of Americans, give or take a few, will have an IQ somewhere between 80 and 120. Do you know if I find the average height of an American and the standard deviation, I can tell you if I go 2 standard deviations either side of the mean, I can tell you that 95% of Americans have that height range. Now, IQ doesn't really change from one country to the other. People are just as intelligent or as dumb if you're French or German or American or Scottish, right? We're equally good and equally dumb, right? But other things do change. Do you know Americans are actually quite tall in the world of average heights? Scottish people are quite small. My height is 5'6". In Scotland, that's about average. Typical Scots adult male is about 5'6". So when you're average, you know, you walk about half the people of your height, half are about, you know, kind of thing. Then you come to America and you like add 4 inches to the average height. So instead of being average, you become short. That's a culture shock. Just to get you some. Now, I don't want to do stereotypes, but I'm not meaning to do stereotypes. But a typical person, can you imagine some countries, a typical person could be quite tall, in another country, typical people could be quite small. So that's okay. Nothing wrong with that. None, being tall or short doesn't matter one iota, really doesn't. But it still exists, right? So there are differences in certain attributes for humans, but intelligence is not one of them. Well, you know, I've still got one more standard deviation to go, don't I? We know that if you go 1, it's 68. If you go 2 standard deviations for the mean, 95% of the data is in that range, right? Well, what happens if you go 3? Well, if you go 3, which is about, what, 70 to 130, from there to there, or in this case, from here to here. Any guesses for I tell you? Because it probably is a guess unless you actually read over the section. If you go 3 standard deviations either side of the mean, so if you go from, in this case, 70 to 130, what percentage do you think it is?
That's what, over 99 is what I'm going to guess.
Cool. %99.7%. That's pretty much everybody, isn't it? 99.7% of the population. The book just calls it almost all, meaning everybody. So we can estimate pretty accurately what percentage of the population lies between any 2 given values, you know, between 1 and 2 and 3 standard deviations. So let me do a pretend version of that story and see what happens. Suppose there was a test, and the test was nice and normal distributed, right? Looks like that. And the mean of this test was 70, and the standard deviation of this test was 8. Now, if the entire class is treated as a population, which it can be, right? The population is everybody in my class, right? So that's allowed. Can't you plug that in and get the answers from your calculator? Because remember, that's just X bar, right? And that's called S, right? So your calculator can get it whether it's a population mean or it's a sample mean. And in this picture here, that guy is going to be 70. And then you're going to go 1, which takes you to 78. 2 is going to get you to 86. And 3 is going to get you to 94. And if I go back 1, 2, and 3, that's going to be 62. That's going to be 54. Yep. And that's going to be 46, right? So can you imagine you were given that, but you draw this picture? Because you kind of need to draw it, I think, to see all the ranges, right? And suppose you were asked, what percentage of students got between 54 and 86 in the test? Well, would you agree that 54 goes there and 86 goes there? How many standard deviations away from the mean is that? Is it 1 standard deviation away from the mean, or is it 2 standard deviations away from the mean? There's the mean. Is that 2 or is that 1 standard deviation?
2.
Wait, 2. What percentage of the data is 2 standard deviations away from the mean?
95%.
So the answer to that question would be 95% of the people in his class would get a score of 54 to 86. If I asked you, and I'm going to abbreviate it now, how many people, what percentage of the people in his class got a score from 62 to 78? Can you see 62 to 78 is only 1 standard deviation away from the mean? And we know that that special number is 68%. And if I said, what percentage of people in his class get 46 to 94, right? So I don't have to keep writing that sentence, right? What percentage would that be? Who got a score between here and here?
99.7.
Right. And I would prefer that answer, but you might find that you have to just use the word almost all because the book wants you to, right? This is getting kind of interesting, the amount of information that is in this normal distribution, isn't there? So if you've got a nice symmetric, bell-shaped curve thing, and you know the mean and you know the standard deviation, can't you tell like where the mean is? Can't you tell where the start and finish of the data is? And can't you tell things like what percentage of people are in certain ranges? Still not finished. I'm going to go and use the book for the next group of questions because you have to draw another diagram and they just do a better job than me at drawing. So I'm going to hopefully find that one. Here we go. Double check I'm in the right one. Of course I'm not. That's the settings section. Now I'm going to go back out and in and you should hopefully see it. Darn it, you were there a minute ago. Right. Now, this is kind of going back to the start. So here goes. Do you see these 4 pictures here? These are meant to represent some distributions, some population distributions. And one of those, and only one of those, actually counts as a normal distribution. So I'm going to show you the ones that not. This guy here doesn't count. He is not normal. Isn't he skewed to the left? Skewed to the left doesn't count. Remember, you've got to be symmetric. You can't be big on one side and a little bit less on the other. That's what skewed is, essentially. This one doesn't count because it's not symmetric. Would you agree that this side here, actually, it goes under the line as well, but this doesn't count. This has a symmetry about it, but doesn't it also have some extra bumps in it? So that one doesn't count. The one that you might not think is this guy. But isn't this symmetric, and it goes up and it goes down? So D is normal, but not bell-shaped. Bell-shaped's for the curves, but that works. Now, look at this fella. Just looking at that picture, question 3. What's mu, the mean? Don't overthink it. I can't hear you if you're talking. I think I see your lips moving. What is mu, the mean?
Oh,
12. Right. Some of you look like you're hurting your eyes, so I'm trying to see if there's something I can do to make your life easier. Can I make something bigger? Can I screw up my display and make things bigger? Probably not. Okay. I think you're stuck with screwing your eyes. Buy a 42-inch TV monitor and plug it into your computer. You're all rich anyway, right? So you should be able to afford that. Okay. So, okay. Now, if you can't see it, let me try and describe it. It's a nice normal distribution, isn't it? Nice bell-shaped curve. Right in the middle is 12. That is why this guy is 12. Now, the next number to it is 14. So isn't the distance between that one and the next number the standard deviation? So that makes the standard deviation 2. We already have the answer to this fella is 12. So what number is mu plus sigma talking about? The mean is 12 and the standard deviation sigma is 2. What number is mu plus sigma talking about?
14 is going to be one
14.
standard deviation.
Right. So don't overthink it, right? They are as simple as that. And here's a couple of questions. I've done this one already, but we'll cover it. Which one of those 2 pictures, which are both bell-shaped curves, both normal distributions, which one of them has got the biggest standard deviation?
A.
Agreed? Looking at only that picture, would you agree that A has a mean of 10 and B has a mean of 4? Looking only at that picture, doesn't A have a standard deviation of 2 and B has a standard deviation of 1? Do you see, if once you know what to look for, can't you get the mean and standard deviation out of these pictures very easily? Right, the guy in the middle is going to be the mean. The guy next door is 1 standard deviation away. So if the guy in the middle is 10 and the guy next door is 12, isn't the difference between them the standard deviation? Right, if the guy in the middle is 4 and the one next to it is 5, the standard deviation in that case is 1. Here are 4 bell-shaped curves. One of these is a mean of 15 and a standard deviation of 2. But only one of those 4 pictures fits that information. They don't have numbers on them, so the top left, the top right, the bottom left, the bottom right. That probably would be a way of telling me where it is. Which one of those four, if you can read the numbers, is mean of 15, standard deviation A2?
Top right.
Right, correct. Let's check it. Can you see the middle of the hill is at 15? A bit hard to tell, but it is, right? And what's the next number after 15? Isn't it 17? And what does 15 to 17 give you? Doesn't it give you a standard deviation A2? If I was going to do, I don't know, this picture here, right? The bottom right-hand side one. Forget what their question is, but look at that. Wouldn't the mean for this question be 12 and the standard deviation would be 3? So if I give you one of these pictures with a few numbers on the bottom, you know everything you need to know about mean and standard deviation, right? You can read them off, you can do it in your head, right? There's no heavy duty calculations to be done. And there's lots of examples here that you can do in your own time. Now, this is a very cool picture. And I am going to be doing a copy of that picture right now. But while I'm trying to do that, and I'm not good at multitasking, is what this piece of information is doing is showing you half the stuff that I've already told you, and then they've added some more stuff. So, can you see mu in the middle, mu plus 1, sigma 2, sigma 3, sigma? Remember my picture had that. That means start at the middle mu, 1, 2, 3 standard deviations, right? But what about the fact that from one side to the other, isn't that blue 68%? Do you see how it's been split as 34? Do you know from here to here, isn't that 95%? And what they're telling you is that little green piece is 13.5, the blue piece is 34, this blue piece is 34, and that little guy is 13.5. And if you add all of that up, you get 95%. So do you see that they've even taken it and cut it into little, I think of it as pieces of cake. And certain pieces of cake are big and have 34% of the whole cake is there. And some are bits of cake. Oh, look at that tiny little piece at the end. You see it's only got 2.35% of the data, right? So I'm going to do a copy of that picture. And it's a good picture because you're going to be able to use it to get even more refined answers. Do you know the questions I did earlier were simply just one standard deviation either side. So what's the IQ from 9 to 110? It was 68%, right? But now we can do much more precise splits. So that's going to be mu. That's going to be mu plus sigma. This guy is mu plus 2 sigma. If I was you and you have a printer at home, I would print out that picture because you're going to use versions of it all over the place, right? So, especially when you come to do the test, right? Because when you do a test, you might want to have something like that handy. Okay, all I'm doing right now, and I almost forgot to, is filling in the numbers. Now I'm going to come out of this question and show you how you can use it. So imagine that we have a normal distribution, and this is the copy of that picture, right? We have a normal distribution, and I know, let's do the IQ one. I got that one handy. And it looks like this. And right in the middle, you've got 100, because that's what the mean was. And the standard deviation for IQ tests are 10. So you've got 110, you've got 120, you've got 130. Going back the way, you've got 90, 80, and 70. I can get the answer to this particular question. What percentage of IQs are between 80 and 110? Now, I'm going to fill in the little boxes with these numbers. So, an IQ of 100 to 110. 34% of Americans have an IQ between 100 and 110. 34% of Americans have an IQ between 90 and 100 as well. Right. The next bunch was what? Another 13 and a half. And the last bunch is so tiny, I'll just put a little arrow on it. 2.35 goes in here, and another 2.35% goes in here. The way I like to do these questions is, because I'm a visual person, I think of that as being a cake. And I see how many bits of cake do I get. Right, if you start at 80, which is here, and you finish at 110, which is here, don't you get this bit of cake, that bit of cake, and that bit of cake? So what is the percentage? It's made up of this piece plus this piece plus this piece. So you just add together 13.5, 34, and 34. And you can get 68 plus 13.5. And the answer you get here is 81.5%. So 81.5% of Americans, roughly, have an IQ between 100 and 110. Okay, so I'll call that question 1. This is question 2. I'd like to know what percentage of Americans have an IQ between 110 and 130. Now, what pieces of cake do I get here? Well, don't I get those last two pieces of cake? That piece and that piece. And that piece there is 13.5% of everybody. And that tiny little piece at the end, there's another 2.35. You add those together and you get 15.85% of Americans have an IQ between 110 and 130. Do you see how this picture, which that's basically just a generalized version, this is a specific example of it. Can't you use it not just to get one standard deviation either side of the mean, 68, 2 standard deviations, 95, and 3 standard deviations, almost everybody? Can you see you can get a little bit of the one and a lot of the other, right? You can have any start number you like and any finish number you like. Great? Right. I'm going to give you a few seconds to try this one out then. I would like to know what percentage of Americans have an IQ between 80 and 130. So if you've got a calculator handy, that's great. If not, I guess you're just going to have to try and do it in your head or a piece of paper. Which pieces of cake do I get to eat? Essentially, that's the way my brain works. Well, don't I start here? So I get this piece of cake, this piece of cake, this piece of cake. Do I get this one? Yep. And do I get that one? Yep. So essentially, shouldn't I be going 13.5, 2 lots of 34, another 13.5, and finish with a little 2.35, right? Would you agree that's all the pieces that make that range up? That ends up being 97.35. I hope. Did somebody agree with me? Because I'm kind of doing me. Oh, great. For a change, I got the calculation right. It's pretty powerful, isn't it? Just tell me its mean and its standard deviation and say that it has this shape. I can tell you where it starts and finishes. I can tell you where the mean is. I can tell you, you know, what percentage of people are from here to there, from this number to that number, from one. I can do any combination I like now. And I can then give you a pretty good estimate of the entire population based on just two pieces of information, mean and standard deviation and its shape. Right? As long as it's normal, distributed, I can do that. That is a pretty, try to think of a good verb for that. That's phenomenal that that much information is contained in such little numbers, right? 2 numbers, yet it's got so much information in it, right? This is fixed. Do you know it doesn't matter if mu is 20 or 2000? It doesn't matter if sigma is 5 or 50. You just rearrange these numbers according to that, and this interval thing stays put, right? It's still 34 for the first pieces of cake, and the last bits are so on. So let me see if I can catch you. So I'm warning you up front, this is a trick question. So in this particular story, the mean is 30 and the standard deviation is 3. Can we say that's kind of old hat? We can do that without thinking that. Here's the trick. What percentage of people have a, imagine it's a quiz score greater than 30? Any ideas? I did give you a heads up that you've got to be
50%?
careful. Say again, Daniel.
50%?
You nailed it. Now you might say, well, where's the trick? Why is that a trick question? Because I thought it was 50% as well, which is good because it's correct. If you add up these 3 pieces of cake, which is kind of what you might have done, does that add up to 50%? Nope. Because isn't there a tiny little bit over here that nobody tells you about, because that goes on forever theoretically, right? So if you ever get questions that say bigger than this or less than that, will you remember that there's pieces of cake that aren't in this diagram and you have to account for them. So can you imagine then that I told you I wanted to know what percentage of people had greater than 27, right? So it's one of those greater than or less stories, right? So the way my brain would work is, okay, you want all this cake, right? I'm not going to use these numbers. I'm going to just say, that's 50%. Don't I just need to add on this piece of cake? Because if you do the cake counting trick, you'll only add those numbers, and you see you'll be a tiny bit out because you don't have what that little piece there is. Nobody ever writes it down, because technically couldn't you then do 5 standard deviations, and that would be even smaller bit of the cake that's still there, and you know, where do you stop? Cool. You can do the same with the less than, right? Watch out for the piece of cake. Now, what else have I got? Oh, one more thing. I've got this one. I can use it. I've actually got this one. Do you know that we stop at 3 standard deviations? So in this case, we stop at 70 and we finish at 130. Right? That's the normal way that you draw these pictures. Mean 1, 2, 3 standard deviations, right? That's the way you do it. There are numbers over here, isn't there? You know, some people in the world do have an IQ of 140, right? They're whatever, geniuses, right? They may have a label like that. we can use this fella to tell you who outliers are. And it's a lot easier. Isn't outliers anybody bigger than that number and anybody less than this number? Remember, is this an outlier, right? So somebody in your class has an IQ of 142. Are they an outlier? Yes. Somebody in this class has an IQ of 68. He's probably a football player, right? Is he an outlier? Yes. Somebody else has an IQ of 85. Is he an outlier? No. Share something with you about IQs that a lot of people mistakenly think what IQs are measuring. A lot of people think IQs are measuring how intelligent you are because the name says it's intelligence quotient. That's what the IQ stands for. You know, oh, an IQ of 130 means you're really intelligent, and an IQ of 80 means that you're kind of dumb. It doesn't measure that at all. And it's a misnomer that it measures it. What IQ tests really measure, and I wish they didn't have the word intelligence in their name. They should have put a different word there. And what they actually measure is how easy it is for you to get and understand knowledge. Right? So you might know people who pick something up, like you tell them at one time and it clicks and they got it, right? That person would probably have a very high IQ. And then you have other people, and I'm included, especially when it was English, had to work really hard to get the idea in to make sense, right? So IQ doesn't actually represent one thing. Sometimes it depends on what you're learning. You know, some of you can look at a car engine and just be shown once where this goes and how you take that out, and boom, you've got it. And me, I'd have to take a video and write down tons of notes because I forget half the stuff, right? So it's not even fixed, right? It's just your ability to learn things easily or not. But if we do it in the academic world, which is kind of where they come from, it's not even a very good measure of how successful you're going to be at university. I personally have met at university students who were extremely high IQs. They were also extremely lazy. And they weren't actually that successful. In fact, I knew one who was at the first year with me. This guy was bright. This guy was sharp as a needle and as lazy as a brick. And so he never worked at anything, and he never done anything. And he failed, and he dropped out. The most successful students that I've met have not always been the bright ones, for want of a better word. It's the ones who had to fight really hard to learn anything. But eventually they stuck it and it made sense. Now, why is that a strength? When you go to university, some of you might, the first class you're going to go to is going to be very difficult, whatever it is. But all your classes have been very difficult. So don't you just stick down and start, reading up stuff, checking the internet, going to tutoring, do what you do, and you get it. Do you know what a bright student does? They can get away with that. But don't you eventually get to something that's hard, even for them? They have no skill set. They've never found something hard. So very often they crash and burn. And they say things like, it's stupid, I never wanted to learn that anyway, and they walk away. But if you had trouble, what's the problem? You won't notice any different. You've always had trouble, right? You see you're learning, and that's a good skill to have, right? That just stick in and figure out how to do it is going to probably do you more good. I'm a great believer personally that I have learned much more from the things that I did wrong than I ever learned from the things I did right. So I drifted, as I do. But we go back to this. Good stuff. Right, let me jump in, show you a few more questions from the textbook, or from the homework, I should say. And these questions might start to make sense now. So you're looking at one of these nice, pretty coloured pictures, better than mine, right? And this question says, what percentage of women are taller than 61? Well, unfortunately, you have to go up here. Do you see 61 would be that number? And standard deviation is 3.1. So can you imagine that was 61 and that was add 3.1 to 61 and then another 3 and off you go. But this question's not as bad as that. Isn't 61 there? So what percentage are taller than it? 50%. What percentage of women are shorter than 61 inches? So can you imagine that mu is 61? What percentage are shorter?
50.
Yay, good. I know the easy questions, but it's worth it. Right, what percentage of women have between 57.9 and 64.1? Now, if you have this picture and you actually write the numbers underneath, can you trust me that that guy there is 61, and this guy here is 64.1, and this guy over here is 57.9? Do you see you're just going to add up the two blue bits of cake? Right, so this side here would be where 57.9 would be, right? And this side here, that number underneath it would be where 64.1 is. And between the two is what, 64. So can you imagine you're going to get a question where you start at this blue one and you finish at this green one? When you add up those three bits of cake, and that'll be that one, that'll be that answer. Can you imagine one where you start here and you finish there, you'd add up these three? Maybe you start way over here and you add only these two, right? So that's the bit of cake analogy that I'm talking about, right? But if you want to do this question, you probably should draw a little sketch of this and note with all these weird sigmas. Shouldn't you write 61, 64.1 and write the numbers underneath so that you can match it with these questions? And if you do that, it comes out really good. Did that make sense, or do you want me to draw a version of that? Does it make sense? Okay, good, because this guy here is an exact carbon copy of that question, just with different numbers, right? So just more practice. And this one here is more practice. So you see, we're wanting you to get good at this, right? Now this one kind of turns the story on its head. The average age, or the average age of the piece of wood is 1241. And the standard deviation is 35. What range of years would give you 68%? Well, wouldn't you take the mean and subtract a standard deviation? And wouldn't you take the mean and add a standard deviation? Actually, you wouldn't write the calculation, wouldn't you write the answer to that calculation? Right? What if you wanted 95%? You'd start with the mean 1241, but wouldn't you take away 70? That's 2 standard deviations. And then on the other end, add 70. And if you want, oh, there they go. You see that word almost all that they sometimes use there? It's being used there. Wouldn't that be 3 standard deviations added and 3 standard deviations took away? So does that question make more sense now that you kind of put it back in the English? Right, and then we are on to pieces of pie, right? Pieces of cake. Is there anything from what we've done as we've scanned through that you feel you want to ask me about, or do we feel good about that type of question now?
Would you mind going over 12A?
Right, estimate the probability that a machine will overflow an 8-ounce cup. Okay, so let's see what the picture is. We have, I'm writing this down, you'll see it in a minute. We have 7.6 is the mean, and the standard deviation is 0.4. And I'm going to be doing 7.6, right? Estimate the probability that the machine will overflow an 8-ounce cup. Okay, a vending machine automatically pours soft drinks. Okay, so I now know what they're on about. Okay, I'm going to leave that guy and show you the picture. Okay, very crude, but the pictures don't need to be detailed, right? That's the guy. Standard deviation. So won't you get 8, and what, 8.4, and then what, 8.8 going that way? And then if you take them away, you get what, a 7.2, a 6.8, and I believe a 6.4 going that way. And this question was, what percentage will be over 8? The overflow is just their way of saying, look, if you put an 8-ounce cup there, you're going to get more than 8 ounces. It's going to, you know, flow over the top, and you go, ouch, that was a mess. I don't like this machine. So in my picture, they want to know that guy, right? On this general picture, don't they want to know that guy there? But I'm not going to get that guy there because that's too much work, because isn't there a bit missing that I don't really know what it is? So I'm going to do this. Can't I find this fella here and take it away from 100? Wouldn't that be the same thing? So I'm going to do 100, take away this guy. Well, if I put a little line here, how much is all of this piece? The whole thing. From the middle all the way to the left. Everybody to the left in the middle. Agreed? How much is this little piece of cake here? Agreed? So isn't all of that half a cake plus 34, which I believe adds up to 84? So the bit I was wanting, that's what we want, isn't that 16%? So that's kind of the strategy that I would have used for that one. If it's areas that are pieces of cake, just add them up. But see if it's one of those bigger than this or less than that, you have to kind of adapt, you know, as I did in this case here. We cool? Right, I'm about to move on to the next section if there's no more questions. Are we cool? One last time? Right. Let's look at chapter 6.2 now. We're still on the normal distribution. In fact, chapter 6, the normal distribution is going to be there one way or the other all the way through. So it's a big deal, right? Suppose I have a mean of 30 and a standard deviation of 5. And this was class A. So class A got a quiz. Their mean was 30 and their standard deviation was 5. And there was another statistics class and they got a different quiz and their mean is 20 and their standard deviation was 10. What we're going to look at right now is we're going to look at what are called, well, they have different names, and they are called standard scores. It's almost the same word, but I'm putting it anyway. Standardized scores. I prefer Z scores, and sometimes they're just called Z. This new guy, this new standardized score, the Z score as it's called, is a way that we can use to compare people in two distinct groups. So I have this class taking a quiz, I have that class. Who knows, maybe the quiz is out of 50, right? Who knows, doesn't matter. This class got an average of 30, but the standard deviation was 5. This class here got an average of 20, the standard deviation is 10. I'm going to try and do a very crude picture of that data. And I'm going to try and do it in such a way that the scales are the same. So I'm going to go 0, 10, 20, 30, 40, 50, right? And same scale, 0, 10, 20, 30, 40, and 50, right? Now, this fella here has a mean of 30. So the hill's going to be at 30. And isn't the standard deviation 5? So 25, 20, and 15, won't that be the kind of shape? Didn't do a very good one. And if you go the other side, it's going to be 35 is 1, 40 is 2, and there's 45, that's 3. So the shape, I'm going to pretend that I did a better version of that shape. There. Can you pretend that red line's not there? It looks much more like a normal shape now, doesn't it? Now let's look at the other group. 20. Okay. That means the top of the hill is going to be at 20. They go 10, 20, 30. Ooh, that was a bad choice. Some people in this class managed to get negative 10. That was because they were English, and I took more points off than they could score. And in this distribution, it would look very flat and wide. Would you agree? Still normal, right? Kind of hard to draw a normal picture that way, but it can do. So here's a little puzzle. There were twin brothers. James, he was in class A. And James got, let's see, what could James get? James got 35. And his brother John, he only got 30. And they were arguing, who did best? Well, you might say, hey, 35 is bigger than 30. James did best. But let's try and think of that in a different way. Which one of these two scores is harder to get? Because isn't it hard to get 30 in a really hard test? And it's quite easy to get 30 in a really easy test. Right? So there should be a fair way of comparing these two scores. And that's what this thing's job is. It basically takes these scores and it standardizes them so that you can look at each one and say, who is better, right? Which one of those two scores was the hardest to get in the class that they were in, right? So, how do you do it? This is the formula for it. Z is equal to X, take away mu over the standard deviation. Well, let's find out. James got 35. That's what the X is, right? Whatever you got, that's the X. So he got 35. In his class, wasn't the mean 30? And the standard deviation is 5. So he got a Z score of 1. Okay, let's see what his brother got. Well, he got a smaller score of 30, but the class average was 20, right? So it was a really hard test, quiz. And it's going to be divided by 10. And this guy got 1. Well, they were twins. And you know twins do everything together. Aren't both those scores equally likely? In other words, they both did about the same. Now, suppose this Z score was 10 and this Z score was 2. The guy with the Z score of 10 did better than the guy with the Z score of 2. It doesn't matter what the raw data is. Better is just a word for saying it's harder to get that score in this class, right? You may well go to university and you'll get an English professor who says, I don't give A's. Because the only thing that would get you an A would be a perfect novel, right? A perfect essay, a perfect poem. And since you can't get perfect, the best I'm ever going to give you is an A-. God, I would avoid that professor like Blake, but that's me, right? But you can imagine you get a numerical score, right, from each of them. Wouldn't it be really, really hard to get an A off him? And then you get some other professor who says, well, if I like it and it's interesting enough, I give A's. To me, you know, English is a free-flowing thing. It's all about entertainment, interest. If you can write something that catches my interest, it's worth an A. You know, that's, I guess, a valid scoring system. But it would be different, wouldn't it, in both classes, what kind of score you would get for the exact same essay. English doesn't have the same standardized technique. So let's check this one out. I'm going to call them A and B again. A university has one last place for a person, and they decide to use what the person got in their mathematics, right? And they found out that the average math score was 75 in the school he came from, and that the standard deviation was 10. And in this other school, this different high school, the average was 80 and the standard deviation was 20. And they found out what each of these students did in this math class, right? They found out what their final exam was, right? And they found out that this person got a score of 85. And this person here got a score of 85. So now they have to pick which person to, to get into the college. Well, you can't use the raw data because isn't getting 85 in this class easier or harder than getting 85 in this class, right? So you would standardize it and look at the standardized, the Z scores. And a big Z score would be the one that you should pick, because getting a big Z score is much harder to do than getting a small Z score. So Z score for this fella is 85, take away 75 over 10. So that gets me a Z score of 2. And for this person, the other person that wanted to get in, they got an 85 as well, but the average was 80 and the standard deviation was 20. And that ends up being not a very high Z score. Do you see if you pick this fella here? Z score of 2. Harder to get than a Z score of 0.25. Kind of interesting that you've now got a way of comparing two different groups that don't even have the same shared values, right? The means are different, the standard deviations are different. The scores that they get may be the same, they may be different, but you can still match them. In fact, let's suppose this person got 80. What does his Z score look like? Well, 80 take away 75 divided by 10 is 80 divided by 75 is, oh, by the way, that's a Z score of 1. I counted wrong. Is 0.5. Doesn't he still get in? So we've now managed to factor out grade inflation, because you just turn everybody's grade into a standardized Z score. So it doesn't matter, if the average in the class was 90 and the standard deviation was 2, or the average class was, score in the class was 60 and the standard deviation was 10, can't you take each person's score and convert it to a Z score and find out who would be the better? Which one was the hardest, essentially. That's kind of cool. Standardized Z scores. Do you know when you do your SAT, if you ever do it, if it ever exists anymore with the way we're in, do you know that SAT scores are standardized? So do you know the score that you get, which would be your raw score, isn't the one that they actually send to you? They actually send to you the standardized score. And the reason they do that is that, see, every year, isn't there going to be a little difference in the average and the standard deviation of all the Z scores, of all the SAT scores? And so to keep it fair, an SAT score from 20 years ago is worth exactly the same as the same SAT score today. There is no grade inflation because everything gets standardized back to make it all kind of balance out. Now here's a guy that we've seen before. Remember the IQ one? I kind of like it because the numbers are easy for me to remember. Now, in this particular case, the mean is 100, right? And the standard deviation is 10. If I found a Z score for somebody who got an IQ of 100, what would the Z score be? You could probably do it in your head. What would a Z score of 100 get you? And I'll write the formula here just to remind you.
Wouldn't it be 0?
It would, because wouldn't you get 100, take away 100, 0. What would a Z score for somebody whose IQ was 110 be? $110, right? Take away the mean, divided by 10. Oh, 1. What do you think this is going to be? 2. 3. What about IQs less than the mean? Their Z scores also exist, but that won't just be 1. Let's do a 90. If you do an IQ of 90, you go 90, right? Take away the mean, divided by 10. That would be what? Negative 10 divided by 10? Oh, negative 1. So if you want to put an idea, what is a Z score telling me? A Z score is the number of standard deviations your score is from the mean. So your Z score is the number of standard deviations your score is from the mean. So can you imagine if somebody had a Z score of 2, wouldn't that mean that they were 2 standard deviations away from whatever the mean was? And if your Z score was -1, you'd be 1 standard deviation less than the mean. So what kind of Z scores do you have to be an outlier? What kind of number do you need to be an outlier? What kind of number for your Z score do you need to be? 3. Would you agree if you get a Z score bigger than 3, you're an outlier? Or less than -3? So Z scores can tell you who did better when you're trying to compare 2 different results from 2 different populations, right? An easy test and a hard test, right? It allows you to do a fair comparison, right? The biggest Z score is the person who did best, right? Allows you to do that. It allows you to tell when something's an outlier. So if you get a Z score and it ends up being 3.2, right? A Z score of 3.2, you know that number's an outlier. Oh, you're a Bill Gates guy. Your Z score is bigger than 3. Or if you get a Z score negative 3.1, doesn't that also make you an outlier? Oh, and the fact it's negative, doesn't that also mean that whatever your score is, it was definitely less than the mean? Cool stuff. So let's have a little look at, some homework questions eventually. Okay, and I go out. And I go back in. God in Himmel. There we go. Phew. Okay, big section. Do you see it? 22 questions. But there's no review, so that's something, right? So that's it. Okay. We're going to kind of do a recap of some of the stuff I've done. So that's where we're going to go first. So the first one says, which one of these descriptions does a standard score measure? So they're calling what I call a Z-score, they're calling it a standard score, right? That's fine. That's a name. So what does a Z-score measure? Does it measure the number of standard deviations a measurement is from the mean? So I'm going to stop reading because yes. Does a raw score less than the mean correspond to a positive or negative standard score? So it's negative, and they are bigger than the mean, positive. Do you see these are very quick? Pick the dot and off you go. Only for completeness sake, I'm going to ask you this question. What is the Z-score, right? I'm just replacing the word standard score with Z-score, right? What is the Z-score for the mean of a distribution?
Zero.
Right. Remember, the mean has a Z-score of 0. Oh, I didn't do that. I'm glad I do this. What are the values of the mean and the standard deviation of a standard normal distribution? So let me bounce out of this and talk about that guy. He's a one-off question, but it's important, and I forgot to tell you about it. If you take this IQ, right? Everybody in America's IQ, right? These data, right? And these are the scores they got, and this is what it is. See, if you take everybody's score and you turn it into IQs, you get these numbers, right? And what you have got when you do that is the standardized distribution. Now, what number will be in the middle of the Z-scores? 0. And won't the numbers go 1, 2, 3, and -1, -2, -3? In fact, now I think about it, couldn't I just say, pretend those numbers aren't there? Can you see the Z-scores in red would correspond to these positions? That's called the standard normal distribution. Now, to answer their question, forget where it came from, just look at that picture. What's the mean of this distribution? I've seen mouths moving and it looked like it. Okay, that'll do. 0. What's the standard deviation? And I say 1. That's what they were asking, right? In that question that I zoomed out and zoomed back in for. Right, now they know what they're asking. It's a pretty easy question, right? But in fact, isn't any distribution going to turn into this one if you turn into Z-scores? So it doesn't matter if it's IQs, quizzes, the weight of people. These numbers will be different, but won't the Z-scores end up being 0, 1, 2, 3? That's the way the math works. So back to, what have I done? I've lost it again. Oh, here we go. Right, question 5. If you know the mean is 26 and you know the standard deviation is 5, can't you get a Z-score for 21? Right. Now, if you wanted to do that, I'm just typing in what the calculation would look like. A little bracket. Why is that not going in there? Oops, it does. A little bracket. You do the score, which is X, so that's 21. Take away 26. And then divide the whole thing by 5. wouldn't that be the calculation that you would do to turn the number 21 into its z-score? And that one actually, I think, if I'm not mistaken, was 1. That makes sense? So you know the mean is going to be 26 every time in this bunch of questions. You know the standard deviation is going to be 5. Can't you turn this guy into a z-score, right? Okay. So there's a whole bunch of some of these guys down here. Let's do a comparison. Oh, we've lost it. Where are you? Oh, overshot it. Oh God, I'm going to kill this poor person's name. Is it Raul? Is that good enough? Right, Raul. It's hard for me to do some American names because I'm not used to your names. But you'd have problems with Scottish names. Once we get out of this, I'll show you one, just to show you what my life can be like sometimes. Right, anyway, Raul scored 75 on his history test, where the mean was 70 and the standard deviation was 6. So although you can't see me doing this, I'm writing this down. I'm going to find out what his history z-score was. So it would be 75, take away 70, divided by 6, and the answer I get is 56, right? Can you trust me? That's what you get. Now, if we move on, he got 74 in his biology test. But in his biology test, the mean was 70, but the standard deviation was 5. So 74, take away 70, divided by 5, and that ends up being 4/5. So that ends up being 0.8, and the other one, I'm doing that as we speak, 5 divided by 6 is 0.83. So the z-score for his history was 0.83, and the z-score for his biology was 0.8. Which one of those, right, did he do better in? Well, don't you always do better in the higher z-score one? And the higher z-score one was biology. Oops. Because it had a higher z-score. I hope I calculated that right. So you can take two different things, find the z-score, and the biggest z-score is considered the better. But let's have a look at these poor people. Here is a whole load of people, and whatever score they got, we don't know anymore. What we know instead is what the z-score is. So can you see the 6 people? I can tell you who got the average, who scored the mean. And I saw your mouth moving, and that's what I think you said. Agreed? How do I know that's the mean? It's 0. Z-scores that are 0 are means. Now, which of these students scored, which of these students scores on the mean? Which of these students scored on the mean? Oh, which of these students, oh God, I apologize, I misread the question. He got the mean, right? Which ones did better? Well, Robert did better. Juan's did better. And I think Linda did better. How do I know those 3 did better? In other words, got a score bigger than the mean? Positive. And who did less? The guys with the negative z-scores. I'll show you that last bit later. Okay, we need to pause on this point because we're getting a little too far ahead and I have things I need to cover. We've done questions already where you got, you know, the two twins and they got their score and who did better, right? Let's try this fella. Call him John. John got a Z-score of 1.3. And Peter, he got a Z-score of negative 0.5. If that's the only thing, if I told you that they were scores that they got in two different tests, right, two different classes, if that's the only thing I told you, couldn't you say a couple of things for sure? Couldn't you, for instance, say that John did better than Peter? I don't know what he got. I only know his Z-score, right? I don't know his real score, his raw score. But I know he did better because isn't 1.3 better than negative 9.5? Don't I also know that John did better than the average of the class, better than the mean? Because he's got a positive Z-score. On the other hand, don't I know that Peter did less than the mean? Because his Z-score is negative. So we get a fair amount of information just in the Z-scores. Suppose I tell you some more. Suppose I tell you that in John's class, the mean was 20 and the standard deviation was 10. Suppose I told you in Peter's class, the mean was 70 and the standard deviation was 5. Right? Wouldn't it be nice if we could take a Z-score and this piece of information and figure out what you really got in the test, right? The real raw data. Because we do it one way. Can't we take raw data and tell you what the Z-score is? You know, you got 82 in the test and your Z-score is 2.1, right? We've done it that way. But wouldn't it be nice if we could take a Z-score and work backwards and say, okay, a Z-score of 1.3 meant you got this in the test. Well, the formula for getting the Z-score was X take away mu over sigma, right? That's the guy we've been using. If you rearrange this formula, you get a new formula that says X is equal to mu plus Z times sigma. And this new formula is how we're going to solve the problem that we have here. So let's take John. I wonder what he got in the test. Well, X is his test score, right, his raw data. The mean in his class was 20. And the standard, the Z-score was 1.3. And the standard deviation was 10. So he got 20 plus 13. He actually got 33. Okay? Now, what about his friend Peter? Well, his raw data, his X, is also mu plus Z sigma, but mu in his case was 70. His Z-score was negative 0.5 and the sigma was 5. So it's 70 take away 2.5 and that's 67.5. So evidently in this class you can get 0.5s. Is that surprising? That although John did significantly better, his raw data is a lot worse looking. Can you see why it's a bad idea to just use raw data to make judgment calls on how good or bad a student is doing? You see, it's much fairer to use Z-scores. Somebody in John's class, let me try and draw a little picture of John's class. It's 20, 30, 40, and 50. Would you agree in John's class, getting more than 50 is going to be a miracle? One guy might get it, right? Very hard. That's John's class. Let's look at Peter's class. And I'm not going to put them above each other, that's too much work. In Peter's class, it was 70, 75, 80, and 85. In fact, if I go backwards, 65, 60, and then finally 55. If you look at Peter's class, didn't everybody virtually get 50 or better? Did you get everybody in this class, but maybe an outlier, right? One person. So can you imagine if they met up and they said, what did you get in the test? And John said, well, I got 33. And Peter would say, hey, I beat you. I got, what did he get again? I've lost it. I got 67.5. It's almost counterintuitive that that's a better score than this. And better just means it's harder to get 33 in this class than it is to get 67.5 in that class. Make sense? Now, can you imagine that you could use Z-scores as a better way of giving A, Bs, and Cs? I won't look at what you got in the class because some tests are hard and some tests are easy. But I'll look at the Z-scores that you got. And I might decide something like this. If you get a Z-score 2 or better, I'm going to give you an A. Right? If you get a Z-score between 0 and 2, I'm going to give you a B. And if you get a Z-score between -1 and 0, I'll give you a C, and everybody else, I'm just going to fail you. Can you see that that might be a better way of doing a grading system that would totally take out how hard the test was or how easy a test was? It would just be based on pure standardized scores. And that is a version of what's called grading on a curve, where you take the standardized scores of people and use them to decide the ABCs rather than the raw score, right? Because some tests are horrible and some tests are easy. Are we cool? Now, the next bit is going to be some visual stuff and a little bit mathematical looking, but I'll get my head in there. God, is that the time? See what time flies when you're enjoying yourself, right? So let's have a population, mean 50, standard deviation 10, because I just want to keep my number scheme easy to do. And I'm going to draw one of these pictures, right? Suppose I was interested in what percentage of people got a score greater than 72. That's the new problem. We can only use these numbers, and remember the cake, 34% and all that stuff. We can only do it for numbers that are on that number line, right? We can only do it for particular values like this. We can't do it for things like what percentage of people got a score between 33 and 71, right? Basically give me any two numbers you like or any number you like. You can't do the pi counting technique. There must be another way that we can do that. Agreed? It would be nice, at least, if there was another way to do that. And so I'm going to show you what you do. So we would call this question x greater than 72. Right? Mathematically, your score greater than 72. Agreed? If this said less than 80, wouldn't you write that down? And how about between 41 and 51, right? Something like that, a between one. They look weird, but that's how mathematically you write betweens, right? So That would represent people who got a score bigger than 72. This would represent people who got a score less than 80. And this would represent people who got a score between 41 and 51. Are we comfortable with the notation? It's just something you've seen. It's called inequations, right? Inequalities. So we're going to take this data and turn it into an equivalent Z-score question. And there's no particular reason why we're going to do that yet, but later on, there's going to be a good reason why we did that. But right now, you're just doing it because we're telling you to do it, right? So, as X greater than 72 would be the same as a Z-score bigger than, well, bigger than whatever 72 is. So over here, I'm going to find out what the Z-score of 72 is. Well, it's X take away mu over sigma. It's going to be 72 take away 50 over 10. I believe the answer is 2.2. So can you see here, I'm not giving you an explanation of why you want to do that. I'm just saying, here's a skill that I want you to be good at. I want you to be good at taking stories like this and turning them into Z-score equivalents. There's one really cool thing. If it's a greater than, isn't the answer greater than? If it's a less than, the answer is a less than. And if it's a between thing, it's still a between, right? So they never change. So for instance, less than 80, won't that become a Z-score less than somebody? And 80 becomes, let's see what 80 becomes. 80 take away 50 divided by 10, that's going to be less than, Z-score less than 3. We cool? Now, if you're going to do a between, basically, can you see where this is going? Aren't I going to take that guy and make it a Z-score, and I'm going to take this guy and make it a Z-score? So it's not a difficult process, right? You can take these questions and convert them into Z-score equivalents. So 41, try to do in my head, is negative 0.9, I believe. Negative 0.9. And 51 is, what on earth is 51? 0.1. So if I gave you a question like, turn this story here into the Z-score equivalent, as long as I tell you who the mean and standard deviation are you comfortable in doing that? I could even do it the other way around. Couldn't I have told you this and you should have been able to convert it back to that? Because wouldn't we use the other formula? Because there's two formulas going around. There's the one that gets you the Z-score, which is I've been using a lot, but isn't there the one that gets you back to your raw data, right? So if I gave you these guys, wouldn't you use this formula to figure out who the X's are? And if I gave you the X's, wouldn't you use this top formula to figure out who the Z should be? So far, so good. So let's answer that question. What percentage of people got a score greater than 72? That'd be a nice question to answer. So the mean is 50. So I'll draw a little picture with 50, 60, 70. So what, 72 is roughly about there. I don't need to be particularly accurate. Aren't I trying to find that piece of the cake? Now, I can't do the piece of cake because it doesn't finish at a nice number, but this guy here, oops, he can do this for us. So I'm now going to show you how to do questions like that using your calculator. So this is me, oops, wrong one, apologize, this is a different emulator, go away. This one better work, and I am going to do it on the screen right now. You should be, uh-oh, I've lost it. Right, are you looking at a picture of a calculator. Right. I wonder if I can move that. No, I can't. Darn it. Okay. I want to know the percentage of people who got a score greater than 72. And I'm going to use that calculator and a feature that it has inside it to do that. And I just realized that I'm having technical issues. Oh, here we go. I have a thing hidden under another thing. I need to show you the beginnings of that before I jumped into the calculator. I was too quick for my own good. Right, so we want to know what percentage of people have a score greater than 72. Okay, that becomes the same thing as what percentage of Z scores are greater than 2.2. So you see that Z scores have the same proportion properties. And the calculator is going to find this fella. Now, I'll show you what it looks like before we do it. There's a guy called the normal CDF. And it's going to have 4 numbers in it. And the last 2 numbers are going to be 0 and 1. And 0 and 1 are the mean of the Z score and the standard deviation of the Z score. And this guy here, you need 2 numbers. You need a low number and you need a big number. And even when the thing that you're asked to find is bigger than 2.2, you still need 2 numbers. So you have to figure a way to make that happen. So here goes. A normal CDF. If you want bigger than 2.2, shouldn't you go 2.2 to some number, comma 0, comma 1, bracket. So here's the last piece of the puzzle. If you're going to be bigger than 2.2, 2.2 up to what number could you use? Well, couldn't you go 2.2 up to 5? That would be bigger, right? 2.2 up to 25. 2.2 up to pick a really big number till you get bored. I pick 999. And the reason I choose that is, do you know a Z score of 999 is a Z score equivalent to me winning the lottery for every lottery that is in the universe, every single day of the universe. It's a number that is never going to harm. You're never going to get a Z score as ridiculously big. In fact, isn't a Z score of 3 kind of big? Yeah. So a Z score of 900. So I just tell you 999, live with it, right? It's just my rule. Right, now we can zoom back to that calculator fella, and I'll show you how to get the probability then. So I'm going to, darn it if I can kick in here. So I'll switch the calculator on. I don't know how clear this is, but do you see the button called vars, which is short for variables? In very faint blue, it says distribution there, D-I-S-T-R. Can you see that guy? Distribution. Now, to get anything that's blue, in my calculator, it's a blue button. That I think some of you, isn't that a yellow button or some other color? Whatever color it is. Blue button, distribution. Oh, darn it, batteries went off. Blue button, distribution. Now, do you see that menu? There's a guy called normal CDF. That's the one I want. Pay no attention to anybody else. That's the one I want. So I'm going to hit enter. Now, you can't see it anymore, but remember those 4 numbers that you need to type in? I'm now about to type them in. The first one was the Z score of 2.2. Now you want bigger than 2.2. So I said, look, 999, that represents bigger. Comma, 0, and 1. And then finish with the bracket. Do you see how I did that? 2.2, comma, 999, comma, 9, comma, 0, comma, 1, right? 999, 0, comma, 1. The comma is above the 7 if you're wondering what it is. Right, when I hit enter, the answer that I get is 0. What was that? 0, 1. Let's round it off to 3 decimals. 0.014. Right, I'll kick out of that and write down what we've got here. I clicked something. I didn't mean to click. I hope it didn't do anything bad. Okay, where's my camera going? Oh, here it is. Phew. Right, do you see that decimal that we got? That is 1.4%. In this test here, people who got 72 or more, can you imagine 72 or more is really just that tiny little piece of cake? 1.4% of the class would have got that score. So not many people, right? We go. Let's try doing some more of those questions then. Let's suppose that in Scotland, that the mean height is 6.5, right? 6.5 feet, 6.5 feet, right? And that the standard deviation is 0.5 feet, right? And I would like to know what percentage of Scottish males, adult males, have a height between 5 feet and 6.2 feet. For no particular reason, is I just want to know, right? Now, that in X data is 5 to 6.2, agreed? Now, if I want to use my calculator, don't I just turn this guy into a Z-score? So, let's see what the Z-score for 5 feet is. On my calculator, if you go 5, take away 6.5, and then divide the answer by 0.5, you get the answer -3. And now I'm doing 6.2. You know, Scottish people aren't 6.5 feet, but it would be nice if we were. So I'm going to go 6.5, take away, sorry, got that wrong, 6.2, take away the 6.5. And now I'm going to divide that answer by 0.5, and I get -0.6. And then I'll go to my calculator, and I'm going to do a normal CDF from -3 to -0.6, 0 and 1. Do you see you just finish with 0 and 1 each time? That's the guy that's going to give me the answer to this question. I'll see if I can make this happen. If you've got an emulator, or even better, if you've got your own calculator, you could maybe go along with me and we'll see how it works, right? So it's going to be second button distribution, menu choice 2. The first number is -3, comma, -0.6, comma, 0, comma 1, finish the bracket. That's about what, 0.27? Or if this fantasy story was true, 27% of Scottish people would be somewhere in the range of 5 foot to 6 foot, 6.2 feet tall. Kind of cool. Yeah. Let me do one more of these guys, and then we'll start looking at some homework questions again. Come on, behave. My computer seems to be getting slower and slower for some reason. Here we go. I'm going to go to my favorite distribution, my IQ test again. We already know that answer. Isn't that answer 34%? Okay. Now that's a mean of 100 and a standard deviation of 10, right? If I wanted to know what percentage of people had an IQ between 100 and 110, that would look like this. Right? Can I turn that into 0 and 1 really easily because I picked really nice numbers? We're now going to find the normal CDF for, sorry, a z-score, right, between 0 and 1. So 0 and 1, 0 and 1. Nice kind of symmetry there. If this works, should the answer be 0.34, roughly? Right, 34%? Well, second distribution. Number 2, what's the probability you get a z-score between 0 and 1? And the mean of the z-scores are 0 by coincidence, and so is the standard deviation. And the answer is, would you agree that's 0.34, 34%? So if you're wondering, where did the 34% come from? Can you see where it came from? If you did, do you know those, the cake one that's cut into bits? See if you wanted to find any one of those little pieces, do you know you could do this now, couldn't you? And yeah, whatever the various pieces are, they match up. Are you comfortable about using this to calculate percentages of awkward start and finish numbers, that you turn them into z-scores and you use your calculator? Do you want me to do some more of those, or do you feel comfortable with the process? Is it one thumb up? Are we good? Do you want to see more? Okay, thumbs up. I'll take it. I think I'm going to have to stop this fella and go back in because we're looking at homework now. I want to see if we can look at that and then maybe finish off with you know, stuff about the midterm. Okay, I'm doing a view on this fella. Oh, it is getting really slow. I'm staring right now. Ah, finally came through. Do you think computers get tired like me? Just if you have them on for too long, they slow down. Okay. Right, so here you're looking at those questions that we've done. See where you take this and you convert it to the equivalent z-score, right? So we've gone through that, right? We've done a little bit randomly. See x less than 30, right? In this story here, can you see that the mean is that number and the standard deviation is that number? So can you imagine x less than 30? You would just say, what z-score does 30 give you with the mean that's this number and a standard deviation with that number? And I strongly suspect it's some horrible decimal, right? Oh, it is. because you've been asked to round off your answers to 2 decimal places. Now, this is not right, but can I just pretend it's 0.12, right? Whatever it really is, you would find out. Are you comfortable about how to do that fella, right? How would you do the reverse? How would you take a z-score and turn it back into x's? Well, wouldn't you use that x equals mean plus z-score sigma thing and just turn them into that? So aren't you really just taking x's and turning them into z's, or z's and turning them into x's, right? And it's just a skill building exercise. They're not really asking you to understand why you're being asked to do it. They're just saying, look, this is a cool thing to be able to do because you're going to use it later. And here is a whole more of the same kind of thing. This one's a little bit different, so I really should do this. All good. You have got 2 different groups. It's a bit messy, the naming system, but mu1 is the mean of the first group, right? It's just a way of mu1 is the first class and mu2 is the second, right? So they're labeling them to make it a little easier. So the first class, the mean is that number and the standard deviation is this. And the second site has this mean and this standard deviation, right? So if you wanted to turn x1 into a z-score, wouldn't you be using this fella here as your mean and this fella over here is your standard deviation? And then you get your z-score. And then wouldn't you do the same for the other one? It's a bit like, remember the John and Peter, which one did better? So you'll find the 2 z-scores, and I'm making no attempt to say I know the answer, but pretend this one was that number, and pretend this guy was that number. Then wouldn't x2 be a much more difficult score to get? So x2 would be a further z value from 0, the more unusual it is, right? Big Z scores mean it's hard to get, right? Now it's asking you here to do some sketches and then get your answer. So I guess I should look at those fellas. And there's a whole bunch of them, but they're basically the same, yeah, they're the same questions in different forms. So for the last thing that we need to cover today to make, you know, the homework doable is draw pictures of various inequalities with z's, which isn't a big thing, and then use your calculator to get the answer. So z greater than 1.2. If you want to draw a picture, isn't 0, 1, 2, 3, minus 1, minus 2, minus 3. Do you know, if I was sensible, I would do one of these and print out 50 pages of them. That way I could keep using this picture. Anyway, z bigger than 1.2. Would you agree it's roughly about there? And that's the picture they want. We will not see that picture. It won't be in your homework. The only thing you're going to tell me is what percentage of data is bigger than that. So we are looking for z bigger than 1.2. And then you're going to get another question, and it's going to be z less than 3.8 or something. And you're going to draw this little picture, and I'm not even going to be accurate anymore. Won't it be this guy here? I haven't even drawn a symmetric picture, but do you get the gist of what the picture's meant to say? And then the only one other example that you can really get, couldn't you get a z between 1.3 and negative 0.3? So if you put a 0 here and you say that's about 0.3 and that's a little bit further away, aren't you really looking for that guy there? So now we need to, and I think I'll write these guys down again. Now we're going to, how do you get what percentage of z-scores are bigger than 1.2? How do you get what percentage of z-scores are less than 3.8? And lastly, because there's only really 3 versions of this question, what percentage of z-scores is between that. That's where the normal CDF comes in. So I'll do this one first because it's actually the easiest. You're going to get normal CDF. Oh, by the way, do you know that a lot of this is done on your calculator? So the only thing that you can actually show me is a very crude picture, which I don't care if it's crude, and this normal CDF thing. In other words, write down what you were typing into the calculator so I know what numbers you were trying to use. Now, in this case here, remember what the convention is. Small number, right? Low first, big number. And it's always 0 and 1, isn't it? You don't need to think about it. 0 and 1 are the last two. And that's what I would type into my calculator. What about this one? Well, won't it be a normal CDF? I'm going to finish with the 0, 1 because I know them. I need a low and a big, right? A low number and a big number. Less than 3.8. Doesn't that mean 3.8 is the biggest number you're ever going to have? Now, I did a version of this guy. When I did this version, didn't I use 999 as just a number to go to? What kind of low number am I going to use on a Z-score that theoretically, right, continues that way forever, right? Would you agree it has to be a negative Z-score, right? Anybody got a thought to my arbitrary number that you always use? Yes, I see mouths move. So that's what you do for a less than. And the last possibility, so there are only 3 to remember, right? 3 situations that you need to deal with. If you want bigger than 1.2, don't you do 1.2 and bigger and finish with a 0 and a 1. So this is going to tell you, once you do it in the calculator, the percentage of Z-scores bigger than 1.2. This is going to tell you the percentage of Z-scores less than 3.8. And this one's going to tell you the percentage of Z-scores between this number and that number. So I'm going to kick back to the calculator. Okay. Go away, whatever that is. Clear these out. Okay, number 2, in. The first one I've got is 1.2 and bigger. Comma 0, comma 1. And that's going to happen about, what, 16% of the time. So 0.16, which is 16%. So 16% of Z-scores are bigger than 1.2. Go back in a second time. Choice 2. And this time I'm going to do the less than 3.8 one. So less than 3.8, comma 0, comma 1. That should be darn close to 100%, shouldn't it? I mean, way over at 3.8 and everybody less than, that's almost everything in the universe. So don't be surprised when this happens. Would you agree that is darn close to 100%? It's 99.9999%. So if I'm rounding off, could I round that off to a clean 100%? And we've got one last one, which is the between one. So second distribution, number 2, and it's between negative 0.3. Oh, by the way, this might harm. That is subtraction. This is negative. Don't use that when you should be using this, right? So negative is this one.
I can't see anything. I don't know what you're...
Oh, God. Have nobody been seeing this for the last 4 minutes?
Sorry.
You're a pain in the butt, class. I used to like you. I'm going to tell my wife on you. You let me rant on like I knew what the heck I was talking about, which I guess I do. And you didn't interrupt me. Is that just because you've got such good manners? Well, I'm not going to do the questions again. Can you now see the calculator? Right. I will do the last one. I'll be generous with the last one if I'm allowed to. No, I'm not. Okay. Can you see how I typed in the first one and got that number? You can see I typed in the second one and got virtually 100. Right, I'm about to finish this one off. Negative 0.3, 1.3, and you always finish with the 0 and the 1, right, in this type of question. And that's going to happen about, what, 52% of the time. So we started today by looking at this normal distribution, right? It's a nice symmetric curve. There's got a mean of 100 or whatever it might be. It's got a standard deviation of 10, whatever it might be. And although they may have almost unlimited variations, don't they all end up behaving the same way? 1, 2, 3 standard deviations, there's fixed amounts. Can't you turn all of them into z-scores and calculate what their percentages are using the calculator? We spent a little bit of time in saying, okay, suppose you want to compare two things, but they have different means and different standard deviations, and the people got different scores. We found a way that allows us to compare two different results in a fair way, right? The z-score. And the rule is bigger z-scores are better, right? Typically. Are we good? Right, so I'm closing off that fella. I am going to take a screen grab for attendance, in case I forget. And we're going to talk about your midterm now. Oh God, this computer's driving me crazy. I'm bouncing out. I have two screens. So if you wonder why I'm playing like a yo-yo, I'm looking at one screen and then I have to look at another because certain things appear on different screens. And that's just my life right now. Okay, so let me go into this one. Are you looking at the Zoom class? Zoom. Are you looking at your Canvas class? Okay. Now, your test, your midterm, is going to be on Monday, and it's going to be on Monday, and it's going to start at 5 and it's going to finish at 8. So turn up at 5, so you don't miss any time that you can do it. And it's on WebAssign, so you just go in like you do a normal homework. You won't see it right now. You won't even see it at 4:55 p.m. So don't panic. It will appear at 5 o'clock because it's timed to appear at 5. It's also timed to disappear at 8. So if you're still in the midterm exam, it's going to kick you out at whatever question you are. So don't dilly-dally, right? Get it done, get it in. But that's only the beginning of the fun. Once you've finished, you have another hour to do this fella, to upload your working. You're going to get questions in WebAssign and you're going to put the answers into WebAssign. But your main grade, where you're going to get your points, is going to come from me looking at your working. So you show me every piece of working that you can. A couple of reasons for that. One is to stop cheating. If you give me the answer to a question that I really know that you have to do a whole load of stuff to get that answer, and you just miraculously said 42, that is not good news, because I'm not going to give you the points for that, because you haven't proved to me you did it at all. For all I know, you just found a question like it and somebody else told you the answer, right? So I'm not doing that. Now, there are exceptions to that. Do you know some questions you have to pick a picture? I don't expect to see working for pick a picture, right? And do you know some questions, especially like the ones we did today, do you know the only working I'd likely see is the normal CDF with the numbers that you used, and maybe a couple of Z-score calculations that you used to get those numbers. And of course the answer, but the answer will be in the thing. The working that you do will help you. WebAssign is not very good. Do you know if the right answer is 1.24 and you did 1.23 because you rounded off badly? Do you know WebAssign's probably going to say you're wrong and give you 0 out of 20? But I'm going to see you're working and I'm going to say you got it right or near enough right. So I'm going to give you 19 out of 20 or 18 out of 20, right? So anything that I can see, I can grade. And I go through your entire working and I adjust your grade that WebAssign gives you based on partial credit. So I want to see your working because it stops anybody cheating, and I want to see your working because it gives me the opportunity to give you more points. We all like points, right? Points are prizes. Now back to this, you finished it. It finishes at 8. I haven't done it yet because I've just been overwhelmed, but this page that you're looking at will change quite a bit. I will minimize it down to the bare minimum. There will be a link to a Zoom meeting. So during the final, there will be an open Zoom meeting, just like this class. And I will see you and I will be able to tell, at least for the ones I can see, that there wasn't your big brother behind you helping you. Secondly, if you come across a question that doesn't make sense or you would like clarification, just pop into Zoom and say, hi, I'm looking at question 14. It don't make sense to me, or what are they asking for? And if I can help you, I will tell you, and then you get back, right? So that's what the Zoom is for. And then finally, whew, you get a hold of this program here or something like it. Has anybody, why is this not loading up there? Here we go. This is one version, you can do anything. Basically, you take pictures of your working, and this program called Adobe Scan will turn them into PDFs for me. And if you've got 8 pages of homework, it turns them all into a PDF and it puts them together really nicely as a single PDF. And then what you do with that is you send it to me. And let's, oh, by the way, can you actually see that thing I just clicked? Can you see a link to download Adobe Scan?
Yeah,
Okay.
never links.
Okay. See, I'm never sure based on what's happened today what you're saying, because you lot are so polite to say, I don't know what he's talking about. I can't see a darn thing, right? So, are we, oh, whoa, what did that do? Yeah. Are we back now to the main one? So you've done your you've done your test, you're ready to go. The last thing to do is copy it as a PDF, and then you hit this fella, boom. And you can't see it because it's not set up, but roughly where my mouse pointer is, top right hand corner, there will be a button that will be called, I believe it's called upload. In fact, I know what I can do. I'm going to go into student view, and I may have to come back out and again. Can you still see the same thing, but it now says you're currently logged into student view? Right, now, this is what you would see when you click on this. Oh, see that big red submit assignment? You will hit it. Oh, by the way, this is a video that takes you through these steps in case you're wondering what this video is about. Now, do you see this thing here saying choose file? Click on it. Now, this is my file, so you can see, well, it looks like it's my Calc 3 stuff, but you should have your PDF stored somewhere, I don't know, in the documents folder or on your desktop or wherever it is, and you click on it. Let's say it's that one. And you hit open. And you probably want to wait a few seconds just to make sure it loads totally. You see it's loading here? And then you hit submit assignment and it's done. That's how I get your working. Now, let's suppose you do it and you say, oh, flipping heck, there's 2 pages of working. I didn't notice them, they were underneath my book or whatever, right? Redo the whole lot. Don't just do the extra 2 because that makes my life really hard. Plus it'll rub out that answer and what I'll get instead is 6 pages and then you rub it out with 2. What we want is 8 pages, right? So do it from scratch, bum, 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 8 pages, go back here, resubmit assignment, and go through the same process. So if you miss a page or something, easy to fix, right? Are you comfortable with the process? WebAssign, just like you do as normal, it'll appear at 5, it'll disappear at 8. Do every bit of working you possibly can, because working points make prizes, right? If I don't see working and you're wrong in WebAssign, you're in real trouble because you're getting 0, because I've nothing to, give you partial credit for. So get the working done. Once it's finished, you use that program Adobe Scan. There's another link for it. It works in Android, and I think it also works in Apple Mac, whatever you call them, the Apple phones. You might have a printer with a scan facility. Do that if you like. That's fine. You might have, because you've taken other classes, got your own program that takes pictures and turns them into PDFs. Great, use that. I don't care who you use, just get a PDF. If for some weird reason your computer just decides to not behave, don't do this unless you have to, but send me an email with your PDF as an attachment. Now, I have something like 120 students. I do not want to go hunting for 120 emails with 120 attachments. So that's your bottom line. I'll only do that if this thing goes wonky. I can't guarantee that Monday Canvas just decides to go on holiday and nothing works, right? Or it might just not work for you. Have you ever had that? It just doesn't want to do what you want it to do and everybody else. So that's your backup plan. I need to see it. Now, your test, your midterm test, is based on everything that we've done. So that's chapters 1, 2, 3, 4, and 6. There will not be any questions, because I'm fed up with the book. I think it was 2.1. Wasn't 2.1, they just didn't want to behave with the nice intervals on the histograms? I'm just not going to ask you one. It's not worth the effort, because all the questions that I've seen have got really ugly intervals, and I think it's unfair because it's not realistic. So I guess you can say 2.1, and at least the histogram part of 2.1 is not going to harm. I might find some question that's nothing to do with histograms that you could do, right? I don't know how many questions, if that would be your next question, how many are in the midterm, because I haven't made it yet. I'm waiting to the weekend when my brain is fresh, because if I made a test right now, God, who knows what would be in it. Because if I'm really doing it, I have to do the question and then I have to do the answers. So I get an idea of, oh God, I don't want to do that one. Those numbers didn't come out the way they should. Or that's weird, I don't like the way the book asked that, right? Well, I don't always know that until I actually do the question. So I'd rather do it fresh. But it does have a really cool feature. Every question I pick will be very similar to your homework, so you won't see any shocks. But it also tells me how many minutes a typical student took to do it. So although I'm giving you 3 hours, I always make sure that it only takes 2.5 hours for the typical student to do. So you shouldn't really be rushed. Right, so I wouldn't worry too much about, I won't have enough time, unless you have issues with time management. And I hope you don't. That's fine. In fact, if you do have issues with time management, here's a couple of tricks. Trick number 1. Do a quick scan through the entire test and do the ones you know how to do first. Because you'll do them first and you'll do them quick and you'll get good points, and won't that make you feel better? And then do the horrible ones that you know you're never really good at and you're not 100% sure what you need to do. And that would be a reasonably easy way, a simple way to do time management. Secondly, do not worry if WebAssign tells you that you're wrong. You only get one shot. As long as I see the work in, you might actually be 100% right, it's just WebAssign's been awkward. As long as I see the work in, it's fine. You will not get help features. Let's see a question like it, or any, you know, when you normally do homework, there's little help things like, here's the place in the book you can go look, all that, that will be disabled. In fact, the only thing you're allowed to use in the test is any notes you've got, any notes that I've put in Canvas, any PDFs that you've found that you've in your search of the internet, any videos that you want to watch. But bear in mind, there's a time constraint. If you have to watch a 20-minute video to find out how to do something for one question, you're probably going to suffer at the end when you run out of time. So keep away from that. What you're not allowed to do, can't talk to anybody, can't use e-tutoring, can't go on blogs and say, how do you do this? Because that means somebody else is doing it, right? That's cheating. I'm scanning my brain for anything that I should tell you that I haven't already. Maybe you can ask me questions. Is there anything you're not sure about?
So just to clarify, you
Yeah.
do want us on Zoom while we're taking the
I do
the
want you on
midterm.
Zoom, and I would prefer to have you on Zoom with the picture as another check for that you're not cheating. Now, I can see some people don't do that. They might have the video and they just choose not to because they feel a bit shy about being on video when I do class lessons and things, and I understand that. But I think for Zoom it's okay because I won't copy that Zoom meeting, right? So if you turn up with your teddy bear outfit on, nobody will know because it will never hit the internet, right? So it'll be totally oblivious. There was something else in the back of my head I was going to talk about there, and it totally left me. Oh, I got it. I will be putting essentially the gist of what I just said on a PDF, and that will appear at the top, so that when you come to Monday, and I'll wait until Monday to do this, this top page will only have the link to Adobe, the link to the exam upload, and the PDF that tells you what the heck's going on, and a Zoom link for the Zoom meeting. And so all the other cool stuff will still be here, but it'll probably be down here under class resources. Because you know that you can use that as a resource. Piece of advice, do you know the formulas, the two formulas that we did today, the Z formula and the X-score formula, and maybe a normal CDF with low comma, big comma, 0, 1, it might be a good idea for you to just get some bits of paper, like cheat sheet, and write those key things down so that they're there in front of you when you need to, you need to find them, rather than trying to hunt through, stacks of paper where all your notes are done. So if you go through all your stuff, look for things that you say, oh yeah, that's a formula I better remember, right? And so on and so forth. Give you another chance. Any other questions? Right, well, I'm going to hang around for a little while because some people may want to, a one-on-one homework question help or whatever, or ask me something, and I'm more than willing to do that. Otherwise, goodbye. And here's the scary part. The next time I see you, you will be doing a midterm.
Thank you. See you Monday.
Okay, bye-bye, guys. See you Monday.
I have a quick question.
Sure.
Okay, so when I clicked the link, it would not let me into Zoom for a while, and I didn't get a majority of the lesson. So is there any way you could post a recording so I could watch it tomorrow night and take down?
Yes, is the short answer. These things take forever and a day, but I'm going to make sure that all the Zoom meetings are online. I'll try my darndest to do it tomorrow, but I teach so many classes as well, it gets in the way. I guarantee that it will definitely be on by Friday, right? So this, what we're doing right now will be on Friday. I probably will edit this conversation out because that's just something that you have asked me, but the gist of what you need to know will be here.
All right, thank you. I just want to make sure I have my notes like down.
Okay, that I totally understand why you would want that. We got some other people got some homework questions, and then you want me to go over. That's kind of what this time period is for now.
So yeah, I have a question
Oh,
about the.
Okay, Madison.
Yeah.
I've got Madison first. Go for it.
Okay. So, are we allowed to use like all the PDFs you put on the website and stuff?
Yes.
Okay. So that's all.
Bear
gonna
in
be-
mind, they're going to slow you down.
Yeah.
So you should only use it sparingly. Oh, I've forgotten something. I'll find a PDF, right? If you try and use a PDF for every one of the questions, you'll run out of time.
Okay.
You know, it takes time to upload them. It takes time to read them. It takes time to process it, right?
Yeah.
So yes, you can use them, but I would suggest you do it sparingly.
Okay.
In fact, if there's a question you think you need to look up a PDF for, do that as one of your later questions.
Okay.
That way you won't run out of time and miss a question you could have done.
Cool. Thank you.
Cool. Okay. Michaela, you got a question? Something you want to go over?
I did want to ask, on the normal CDF on the TI-84,
Yes.
I accidentally put in the actual like data, like instead of doing the
And it gives you the same answer?
Yeah, it gave me the same answer. I
Yeah.
just wanted to see, is that true across the board, or was that just the numbers?
It is across the board.
Okay.
But the
Are we
way
allowed to do it?
the way the book does this is they do it with the Z's and the zeros and ones. And I had to show you it that way because that's the way the homework questions are going to work, right?
Okay.
But not right now, but in the later section, they're going to say, hey guys, there's a better way of doing this same question without you
Good.
turning them into Z-scores. And even if they don't, I will have shown you the short way of doing it.
Okay.
I don't have a problem if you did that in the midterm because you're still answering the question, right?
Okay.
But you would still have to turn them into Z-scores because there's a kind of AV where you do the Z-scores and then a C where you use the calculator. So I'm not sure how much advantage it would be to just not do it. But yes, the short answer is it's across the board. It works all the time.
Okay. Thank you.
Okay. Nika, you got a question? Homework?
No, I just looked through the homework to see if I did, and I think I'm actually all set.
Okay,
So,
well, if you're all set, it's bye-bye.
Okay.
And if you're not all set, hang around and ask me something, right?
Okay, see ya. Thanks.
Yeah, if you get, you don't know until Friday that you're not all set, shoot me an email and we can do a quick Zoom lesson. We can go over something. Or if
Okay.
it's something I can
Okay,
answer in
thank
the
you.
email, that'll work as well, okay?
Okay, before Friday. Okay, cool. Thank you.
You're
Right.
welcome, bye-bye.
Could you help me with lesson 4.1 on number 6B?
Number 6C from 4.1,
B.
A,
No,
B,
actually,
C, D.
6B.
Oh, D as in Donald, gotcha.
No, B.
B as in boy.
Yes.
Yeah, our connection, and I'm old, it was hard for me to hear you, but that wasn't your fault. Okay, so I have to leave student view. I think I'm going to have to do a stop and then I'll go back in. Where the heck is homework? I can never find things when I want them. I'll go here. I'll go in here. 4.1, that's the intro to probability questions, right?
I think so.
Yeah, that's where it says here. And it's question 6, so I'll click on that. Oh, I gotcha. Now, the question is, what is the probability that all 4 children are male? That's the question you're having trouble with?
Oh, that's the question, but the part that I got wrong was 6B. The last portion of that.
Oh, notice that the
So the one-
complement. Oh, so it says here, notice that the complement of the events, all 4 children are male. Right, so the opposite of that is at least one of the children is female. Now that's true. Isn't, how do I phrase this, right? If event A is they're all boys, isn't the opposite of event, at least one of them ain't a boy? which is another way of saying at least one of them's a girl. So that's what they're saying. Now, the key to getting the answer to that is actually quite easy. Do you know that if you know the probability of something is 0.1, isn't the probability of what they call its complement, right, the opposite of it, isn't it 0.9? If one of them's a third, the other is 2/3. If one of them is 0.7, the other is 0.3. The relationship here is that an event and the opposite event, right, the complement event, their probabilities always add up to 1. So I believe that the answer to the first part of this question was getting 4 boys can only happen 1 out of 16 times. Agreed?
Yes.
So what's the opposite of event? Well, the opposite of event will happen with a probability of 15 sixteenths.
Oh, I put 4. Did I miss one by accident?
Well, if you were counting, you missed a lot, because at least one child is female. Also means 2 children could be female. Also means 3 could be female. Also means all 4 could be female. So the answer is, in fact, everybody except the 4 males. So I'm clicking the 4 males, but the opposite is the other 15.
So it's 5. So is it supposed to be 5 over 16?
No, 15 over 16.
15 over 16. You should just
Yes.
subtract. Oh, all right.
Right. So see if you get a similar question and there's 8 things there, and one of them is ticked, then that's 1/8. But the opposite of event will be 7/8.
Oh, okay. Alrighty. I have another question.
For sure. What is it?
It's section 4.2, lesson 4.2. Number
Okay, I'll
B.
go back. I'll go back up 4.2. What question again in 4.2?
3B.
3B. So I'll go out and in. Okay. Now I'm going to write this down because you kind of need to see what I'm doing this time. So we got that. And it was the probability of A given B is 0.9. And the question asked us to find the probability of A and B. Is that correct?
Actually, no. It's given PA equals 0.4 and PB.
Oh, I know what's happened. Each time you do this, it generates new numbers. Okay, so what's your PA in this question?
PA is 0.4.
Okay, so my question is different. PB, what's your PB in this question?
6.
6. And your A given B is nothing 0.4?
0.24, yes.
Oh, 2. There's a 2 in there. That's unusual, right? 0.24.
For the part A, it's 0.24.
Oh, I don't want to know
Or
that.
it tells you to compute.
All right. In part B, the question you're having issues with, what did they tell you the probability of A given B is? In my question, it says it's 0.9, but what did they tell you in your question?
0.7.
Okay, now I got the guy I'm looking for, right? Right. Oh, I better show you my working. Okay. Now, the one that you did, I'm just putting this out for completeness sake. Didn't you do the probability of A, probability B, and you got the number 0.24, and that was correct, right? That's what you did.
Yes.
Yeah. Now, if you want to find the probability of A and B, for instance, and there is a formula for calculating the probability of A and B. Right? It's a probability of A given B times the probability of B. And that's just a formula that you'll find in the textbook. And in this case, that guy there was 0.7, right? And this guy here was 0.6. So the answer would be 0.42. So it was just a formula that you needed to use. There are two formulas. If the two events are independent, then it's a probability of A times the probability of B, right? That's what you did in question A. But when they are not independent, right? When A and B interact in some way, then this fella gets calculated by that new formula. It's a conditional probability, A given B times B. There are two versions of it, actually. So it depends if they give you these two numbers or if they gave you these two numbers, which one of these formulas that you would use to get A and B. So when they're independent, you just multiply the two together and it's good. But when they are dependent, they have a connection. And a connection is given by this. See if the probability of A given B, in this case is 0.7. But if the probability of A given B is the same number as the probability of A, then the two events, A and B, are independent of each other, and you get this formula at the top. But when they're not equal to each other, you have to use the second formula.
All right. Thank you so much.
You are welcome. I'm going to kill.
Yeah, go ahead. Go. You can move on to the next person.
Okay, Shuto Haka. I apologize. Shuto Hakata. Am I good? Shuto Hakata, are you there? I wonder if she forgot and just left without closing off. Last chance if you're there. Do you have any other questions then?
I actually do.
Okay.
Okay. So, lesson 4 review. Number 7 with parts B, C, D. Wait, with part E.
Those four?
Just E. So number
just
7, E.
right. Okay, so I'll need to go in. Is it something that you could read to me, or will I probably have to see it to know what it is?
Actually, it's B, C, D, and E.
Okay, so it is B, C, D, and
sorry.
E. I think I should probably go in. There's too much going on there for probably you to say it to me and for me to understand it all. Okay, so I'm going in and I'll do a review, fella. And question 7, kick in. And it's these fellas here. Oh, you can't see it, sorry. Okay, so is this the right one? I think I'm in the wrong place here. Let me close that off. Oh, shooting space. Right. I went in and back out and missed it. Right, it's this guy here. Do you see the guy I'm looking at, which is your question 7?
Yes, let me.
The problem is these numbers may not be yours because the book changes the numbers all the time. Is that what happened to you?
Let me see. Yeah, they're a little bit off.
Yeah, so I can only show you what I would do, but you have to do it with the numbers you've got, right? So the first question you had a problem with was B, right? And it says, what's the probability that you get none given that it's a W? So I have to figure out what W is. W is washing the oil off within 5 minutes. Okay. So that is this column, right? So what's the probability that the reaction was none given that you washed it within 5 minutes? Now, when you wash something within 5 minutes, that means you're being told that this column here, right? This one column, we know that that's all that happened. That tells me that the bottom number is going to be 500. See, if I know you wash within 5 minutes, then you can only be these people here. Now, of these people here, how many of them had no reaction, none reaction? And the answer was 409 people. So out of the 500 who were within 5 minutes, only 409 of them had no reaction. Now the next one says, what's the probability of S, that's a strong reaction, given that they did this? Okay. They still washed their hands, so the bottom is still 500. Now, how many of the people in that first column had a strong reaction to the oil?
33.
And that's that one. Now, whatever they tell you, you see this bottom bit that says W, given W, that tells me that you only pick numbers from the column that W is in. Now, in the next question, they tell you A. And what the heck is A? There's a code over here for A.
Is that after?
Say again?
The after 5 minutes?
No, actually, you would think it should be, but the code for A, oh, I take it back, you were right. It is after 5 minutes. So see when you do the after 5 minutes, do you see you're going to get your numbers only from this column?
Oh.
So how many had no reaction? 53 out of 500, right? 53 out of this 500. How many had a strong reaction? In my table, 106 out of 500. So I would be doing here 53 out of 500. And after this, I would then be doing 106. That's people who had a strong reaction, but only out of that 500. Oh, and by the way, all these calculations need to be turned into decimals that are rounded off to 3 decimal places. If you type in the fractions or whatever, I think you're going to have problems. Does that make sense now?
Yes.
Okay, now N and W. N and W, okay. So what's the probability that you get N and W going on? Well, the probability of N and W is the probability of N given W times the probability of W.
So and means multiply, essentially?
The N is just a code for no reaction.
No, the and.
Oh, the and is a code for multiply, yes.
Okay.
You multiply either the two things separately. So one of our formulas was P of N times P of W, right? And you would do them separately. And the other formula was that second one. Do you remember the one where the two things were connected? And that's what we're doing here. All these things are connected. So that we have to do the probability that N given W, which we already know because that's the answer to B, times the probability of W, which I believe in that table is what, 0.5, because half the people did within 5 minutes. So that's what W is.
Wait, could you repeat that?
I'll try. You're going to find, I'm going to have to go out and in here because it's one of those things I think I can show you rather than say. It's a very visual thing.
Oh, okay.
But I'm going to have to pretend I know what the numbers are because I'm not good enough to zoom back in and out, right? So,
Okay.
so I can use your numbers if you prefer, right?
Okay.
If you want to find the probability of N and W, the formula that we have to use is this one. It's made up of two things multiplied together, right? So and is a multiplication. What is N and W? Didn't we get that from an earlier question?
Yeah, I think it was a 407 over 500.
Right, so can I just pretend that that's 0.3? I know it's not, but whatever that ends up being, you put the decimal here, right?
Sure.
And then what's the probability of W? Well, in the table that I had, there was a W here, and I can't remember A with the other one, and there was 500 here, and there's 500 here, and there was 1,000 people altogether. So if you wanted to know what's the probability that you pick W, isn't it 500 out of 1,000, which ends up being 0.5. So in your question, you're going to multiply, do you remember what that fraction was that you gave me that I pretended was 0.3?
407 over 500.
Right, so you're going to take that guy and multiply him by this guy.